I think we're going to start. So first of all, I want to thank you all for being here. I'm very glad that you all came to hear about this fascinating subject about the interaction of AI, formal languages, and mathematics. So I was supposed to give the introduction talk for the conference, and I didn't know exactly what I wanted to be saying. And then I had an idea. And out of this idea stemmed out this text for the introduction. So, artificial intelligence and mathematics are two of the most important fields of study in the 21st century. As our world becomes more and more complex, we rely on artificial intelligence and mathematics to help us make sense of it all. In the past, artificial intelligence has been used to develop new mathematical algorithms and to solve complex problems in physics and engineering. Today, artificial intelligence is being used to help us understanding the world around us in new ways. For example, by analyzing huge data sets, artificial intelligence can reveal patterns that would be impossible to see with the human eye. Artificial intelligence is also being used to develop new theories in mathematics and to prove existing theories. In the future, artificial intelligence and mathematics will continue to work together to help us solve the world's most difficult problems. Which I think is not too bad an introduction. And can you guess what is the specificity of this text? Yes, exactly. It was generated by an artificial intelligence. And I asked the model to generate an introduction for a conference about AI and mathematics. And I thought it did a very good job. So I wanted to do a control test to see if it was just generic and able to do some introduction about anything that would just switch the words mathematics and AI with the rest. So I asked the model to do an introduction about the conference about the interaction between scuba diving and pastry. And I was amazed by the output. So I'm going to read it to you. I'm so excited to be here today to talk about one of my favorite topics, scuba diving and pastry. When I'm diving, I often think about how the underwater world looks like a giant pastry. There are all sorts of fascinating textures and colors, and it's just so peaceful and calming. And of course, when I'm baking, I often think about how I could incorporate some of the amazing underwater scenery into my designs. I mean, who wouldn't want a cake that looks like a coral reef? So today, I want to talk about how we can use scuba diving to inspire our pastry creations and vice versa. And I also thought that, okay. Yeah. Sorry about that. Yeah, so I thought it was also pretty good for an introduction about scuba diving and pastry. And so I got to thinking, what is the difference between that kind of task and actually doing mathematics? And I don't have the answer for that, but I guess it's closer than we think and maybe further than we think. And I think the crux of the subject and why we're here is exactly that, understanding what is specific to the human activity that is mathematics, and how using AI can make us understand that a little bit better. And I think also, in the other direction, using mathematics as some kind of playing ground to test out new AI ideas, to use new data sets that are of very high quality, will help us understand a little bit better how AI works. And of course, this interaction, I think, is about to grow stronger and more prevalent and relies on this new trend in mathematics of using actual proof assistant to do mathematics. And the reason I'm also mentioning this is because I think it's going to have a deep impact and it will transform in a way that is deep the way we think about mathematics and the way we interact with mathematics and the way people do some mathematics. So I hope that we can touch those subjects today and tomorrow, and I hope that we will learn a little bit more about those aspects, and I hope that you will have fun watching the talks. Thank you very much. So without further ado, let me introduce the first speaker, Geordie Williamson, who's a mathematician from the University of Sydney, and who's going to talk about how deep learning can help mathematicians.
Thank you very much, Aurelia. Can you hear me? Okay. So I'll just share my screen. All good? Okay, so yeah, thank you very, very much for this invitation. The list of topics and speakers just looks exactly what I'm interested in at the moment. So it's really great that you've organized this thing, and it's a great honor to speak here. And yes, apologies that I'm on the other side of the world. And thanks for accommodating me anyway. Okay, so what I'm talking about today is how can deep learning help pure mathematicians? I think I said machine learning in my title. I really mean deep learning. And this is very much the reflections of a mathematician. So I noticed that many speakers are really experts in deep learning. I am not. I'm just trying to come to terms as a mathematician, firstly with deep learning, and also what we can use it for. I think this is a fascinating topic. Also, because of what Aurélien pointed out, that it shines a light on the mathematical process, and I find that really fascinating. Okay, so I just want to start off with a little metaphor. I want to give you two metaphors which try to place how I'm thinking about things in terms of the subjects of this conference. So here's a theorem. There's infinitely many prime numbers. You might have seen this theorem before. I rather like it. Here's a proof. We assume there's finitely many. Then we take their product and add 1. And I'm hoping you know the rest. Okay, so none of the primes on our finite list can possibly divide the number which is the product of all the primes plus 1. And therefore there's a prime missing. And so by induction there's infinitely many. And so I think if you look at this proof, steps 1 and step 3, even though I haven't really given the details of step 3, are routine, and step 2 is not. Step 2 is really an idea. I remember when I first learned this proof, I was really kind of shocked by it, kind of audacious. So where does that idea come from? And there's this quote from Claire Vazin. She wrote a beautiful article recently in the notices about the mathematical process. She writes, there is the monastic introverted period where we are just contemplating the ocean of our ignorance, but then suddenly something happens, the monk becomes busy and excited, in a hurry to look more closely at the details. And her description of the mathematical process very closely aligns with mine. I think people have very different experiences exploring the mathematical world, but Claire's description very much matches what I've experienced. And I tried to make a flowchart for a public lecture some weeks ago. So this is meant to illustrate for the general public what we do as mathematicians. So, you know, I hope you can relate to this. We spend long periods of time totally lost. And then apparently out of nowhere, it's very difficult to say where that idea comes from to take the products of the prime plus and add 1. We get this idea. And many of these branches lead nowhere. Either we see that it's not leading anywhere, or it just fizzles off and we get sick of working or whatever, doesn't look as promising. But sometimes we get a path through this kind of maze and we reach a theorem, and then this theorem is digested by the community, etc. Now, what we're really interested in, I think, in this work is this part of the mathematical process. Where does that genesis of an idea come from? And I think one of the possible points at which that idea comes from is the fact that we're acquainted with many examples and we've done some kind of pattern recognition in our brains, and so we can potentially try to imitate that part of the mathematical process with deep learning. And I just want to point out that at the stage where we have an argument and it might be very complicated, that's when proof verifiers come in. And so I think that FL the title of this conference is FLAIM, and of course everything here is mathematics, but the AI is kind of looking at the start of this process, and the FL is looking at the end of this process, okay, in very, very coarse approximation. And just as another kind of metaphor, so this is something that I remember being really shocked by as something like a 10-year-old. So I'd convinced myself that I could take the square root of a positive real number. You know, I didn't really know that rigorously, but I believed that positive numbers had square roots. And then I remember we had to solve a quadratic equation. And the first way that we do this is we kind of bang this formula into the heads of our students, our poor students. But then at some point we actually understand what's going on. And what we do is we complete the square. And this kind of innocent step of completing the square immediately leads us, so once we complete the square, then we can move one term to the right-hand side and use what we already know, namely positive reals have square roots, and we're led to the quadratic equation. Okay, but somehow this is, why did we decide, we're kind of totally lost. Like as a 10-year-old, I had no idea how to solve this problem. I knew how to take the square root of a real number, positive and bigger than 0. I didn't know how to solve quadratic equations because I didn't have this idea of completing the square. Once you have this idea of completing the square, then it's basically routine. And also, I know that Tim Gowers has thought rather a lot about this, and he has these beautiful examples where there's certain proofs which just are kind of reductive, so you essentially start from the assumptions and then you expand and get to a proof. Then there's other proofs which appear to really need a genuine idea. So he has this beautiful example of showing that a function on the unit interval is bounded. And he explains that in trying to prove this statement, you're led to the notion of compactness. So you're led to an important mathematical concept through proof discovery. So where do these ideas come from? So here's the plan of the talk. So I know that I have no idea what the audience looks like because I can't see anyone, but I'm assuming that about half of you know much more about deep learning than I do. But I assume some percentage of you don't, and would perhaps appreciate, if you're a mathematician, you might appreciate having a mathematician explain in very broad terms what deep learning is. So that's what I plan to do for the first 15 minutes or so. Then I just want to give some simple examples of deep learning in mathematics. These are basically examples where deep learning struggles. And I think they're interesting, and somehow I wish someone had told me these examples when I began the subject. I want to give 5 examples from modern pure mathematics research, which I find interesting, and then I want to give some hints at the end for the interested mathematician if you're interested in pursuing this stuff. Okay, so that's the plan. So if you know what deep learning is, now you can go to sleep for 15 minutes. Sorry, I should first give a disclaimer. I'm a pure mathematician. So basically my kind of world is algebra, algebraic geometry, algebraic topology, representation theory. I'm not an applied mathematician. The vast majority of work in deep learning and math occurs in applied math. And also there's fascinating questions which I also find very interesting about deep learning, like that deep learning raises in mathematics. I'm not talking about that at all in this talk. I've been working with DeepMind for 2 years, so Alex Davies is also speaking at this conference, and Alex will be talking about related work, or in some sense the same work, but it's probably very useful to have a mathematician talk about it and a deep learning expert talk about it. So you get 2 different perspectives on the same world. Yeah, so I just want to emphasize I'm not an expert on deep learning, and all opinions are my own, which also means some opinions are wrong, and then you can tell me about it afterwards. So a crash course in deep learning. So this is what deep learning does very well, recognizes a tiger. We can train a model using 1,000 images. So let's say we have 10,000 images, 5,000 of them are of tigers, 5,000 of them are not of tigers. So what we're actually doing is we're asking for a function which takes in the pixel values, so that takes in a matrix like this and outputs a real number which is very positive if we think it's a tiger and very negative if we think it's not a tiger. Okay? So this is the blueprint of a kind of vanilla deep neural net, or in this case not particularly deep, but so I'm just going over this for the people that don't know what deep learning is. I'll try to make it somewhat intelligible, but of course it's an enormous subject. So we have, so our input is on the left-hand side. So if you just concentrate on the top of this slide, what I'm describing to you is a particular family of piecewise linear functions. Okay, these are functions where so linear should be affine linear throughout. So we take a vector in r to the 10,000, we apply an affine linear transformation to it. We get another vector in r to the 1,000. Now, any entries that are negative, we replace with 0, and any entries that are positive, we keep. That's the rectified linear unit, or ReLU, the nonlinearity that somehow fuels this whole subject. And then we do another affine linear transformation, we do another ReLU, and then we do another affine linear transformation. So this is describing a class of piecewise linear functions parameterized by an enormous vector space, which are basically the coefficients of our matrices. And I guess the point is, so if we're given some target function, or we're given the values of some target function, phi tilde, and we train phi to approximate phi tilde via gradient descent with respect to some differentiable loss function. So you might, for example, a naive thing might be to take the mean squared error. So you're trying to approximate a function, you just take the norm between the value of that function and the value of the test function, and evaluate that at 1,000 points of your test data set or something, and that gives you a measure of how far phi is away from phi tilde, and you try to improve that. Okay. So I guess the two miracles of deep learning are, one, that this actually works, that it converges to something, and secondly, that thing that it converges to often does well off your training data. Okay, so it generalizes in some sense. So here I'll just show you a neural net training. So on the right-hand side, we have the data set. So that's the spiral consisting of the orange dots and the blue dots. That's our training data set. And what we're trying to do is approximate, we're trying to learn this classification into orange and blue dots. So imagine that this data set lives in 10,000 dimensions or something, and we can't immediately see that these are two arms of a spiral. Then we might want a computer to discover that fact for us. And here you can see the neural net. Here you can see the weights are being wiggled. These up here is the epochs, the steps of stochastic gradient descent. And you can see here training is taking place. Here we're evaluating the loss on a test, on a training data set and a test data set, and you can see the training evolving. So this is a lovely little playground. If you're new to neural nets, it's called the TensorFlow playground. You can just play around with different data sets and you can see a good visualization of what's going on. So here, this is essentially a representation of a 8x5 matrix, and we're coloring the coordinates based on whether they're positive or negative and how positive they are. Okay, and you can see that after a while it's doing not too bad. You can see these kind of spikes in training performance. Many features that are present in training in general. Okay, one of the things that I've kind of slowly discovered in the subject is you kind of don't know when to turn it off, etc. Okay, so that's meant to be some kind of picture of what happens during deep learning. Okay. Okay, so just some very, very basic points. You want to use deep learning in situations when the input dimension is very high. So we have a million different techniques for approximating functions on R2, so the previous example is not really a real example. we really want our input dimension to be very high dimensional. For example, the pixel values of an image of a tiger or something like that in a 10 million dimensional space. So I want to just give a picture here. So this is, I think, a very nice geometric picture of what happens during learning. So we divide our space. So this is, I'm drawing R2, but I really want to imagine something like R to the 10,000. We divide this space up into polyhedral regions. So that's each of these regions. And on each of these regions, we have a linear function or an affine linear function. So if you're thinking about, for example, linear regression, then what this is trying to do is just, you have a data set and you're trying to approximate it by a hyperplane. And so your hyperplane's moving around as you do this convex optimization problem. And here what we're doing is we're kind of doing a whole lot of different regressions all at once. And now it's not at all convex, not at all clear that it's going to converge, all very complicated, but it still seems to work. And one very important point in this picture is that there's this small region of space where something interesting is going on, and then if you go off to infinity, it's very boring in the sense that it's just linear. Okay? So you can't expect to approximate some function which is kind of interesting throughout space. You're much more, your function should be interesting on some unit cube. So if you think about the pixel value example, images, because my pixel values are allowed to be between 0 and 100 or something, it lives, I can renormalize so that it naturally lives on the unit cube. And also things like PyTorch and stuff very much expect your input to be on the unit cube. Coordinates have low symbolic content, so what I mean by this is that if you change a pixel value, it doesn't change the output massively. Whereas with a lot of functions that I'm used to in maths, kind of small changes in the input give very, very drastic changes in the output. So I'll give an example in a second. So I like to think of this as being, you want to use this on functions that are kind of more on the intuitive side of human activity rather than, you don't want to use deep learning to learn a cryptographic function or something like that. And the other point that's, I think, useful for people like me who come from kind of the more algebraic side of mathematics is that there's this kind of fascinating thing called the curse of dimensionality, which is basically that something like R to the 10,000 has much, much more space than you could ever possibly imagine. So if you want to approximate a function using standard techniques like, interpolating it from a few hundred values, you're just absolutely out of luck. And in some situations, the miracle of deep learning is that it somehow overcomes this curse of dimensionality. Okay, so now I just want to give simple examples, some simple examples in mathematics. These are both negative examples, so there's many, many positive examples, but I just want to emphasize these examples because I think they're very useful for a mathematician to see. So, if you want to learn about this subject, there's a whole lot of stuff on YouTube where you can, for example, learn how to classify tigers and those kind of tasks, but often it feels to me as a mathematician that there's a kind of mathematical examples are missing. So here's a very simple example. So learning the parity bit. So we take a length 0, 1 sequence of length 1,000, and we want to say whether the sum of its digits is 0 or 1 mod 2. So this is an extremely noise-sensitive function. So this is the checksum in signal processing. Flipping one bit changes the value. And so it's very noise-sensitive. And so it's like every coordinate's very high symbolic content and therefore very difficult to learn. So if you throw a very big neural net and you fix the length of your bit string, it will learn it, but this is not the type of function. You need to try very hard, and it's not the type of function you want to throw deep learning at. This is another beautiful example. So we take a permutation of n, the rearrangement of n, and we list the values of this permutation as x1 up to xn. Okay, so x1 is what a permutation does to 1, x2 is what it does to 2, xn is what it does to n. So for example, the identity permutation is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's two very important concepts in my world, which are both subsets of integers from 1 up to n minus 1 called the right and left descent set. So the right descent set is those I, such that the I plus 1 first element is sent to something less than the ith element. So for example, this would be the empty set for the identity permutation. And the second one is we look at those positions in this string where I plus 1 occurs to the right of I, occurs to the left of I. Okay? So I occurs to the right of I plus 1. This is the left descent set. And from the point of view of permutations, any permutation I can invert, and if I compute these two quantities, they're swapped. So this is kind of, from a mathematician's point of view, these two sets are entirely symmetrical. But what's very interesting is if you think about this permutation, you think about putting it into a neural net, if you put it in using this normalization that I've used here, where I list the values, what it does to 1, what it does to 2, what it does to n, then there's an incredibly easy neural net that I can write down in a second, which computes this right descent set. Namely, I just evaluate xi plus 1 minus xi. And this gives me a real number which is positive if I is in that descent set and negative otherwise, or the other way around. Okay? So if you just look at the way that these points sit in space, there's some obvious hyperplanes that tell me exactly what's going on. Whereas with the left descent set, you have to work a lot harder. And this, you can do it, but you really need, it looks to me like you need something like n squared hyperplanes, and it's rather complicated how to fit all the information together. So it's really interesting to kind of see if this geometric intuition is reflected in the way that the neural net trains, and it turns out it is. So here I just set up a simple vanilla neural net, like I described at the beginning, trying to learn the right descent set. And in about 2 seconds, it gets the right descent set learning with 98% accuracy. If I let it go a little bit longer, it approaches 100. And the left descent set, even if I leave it run all afternoon, it gets 0%. And if I want it to get more accurate, then I can drop n. So if I drop n down to about 10, then after enormous effort, about an hour of training, it'll learn the left descent set. Okay, but yeah, I think it's very interesting because it's pointing out like how the network sees the information is extremely important. So I've kind of biased the way that I'm giving the information to the network by this particular input scheme. So instead I can input permutation matrices. So this is, now I input an n squared vector, which is just the permutation matrix of this permutation, and then I get completely symmetrical learning. Okay, so it learns right descent set, left descent set with high accuracy pretty fast. But in order to do this, I have to drop my n back down to about 20 in order to give my poor laptop a chance in a couple of minutes, okay, to learn this. But I think this is a very interesting example in terms of the representation in terms of how you actually put your inputs into a vector space is very important. Okay. I should also say that I feel like these simple examples are still kind of missing for us mathematicians trying to come to grips with deep learning. So if you have other such examples, I'd love to hear them and love to play with them. It's very fun, I think, to play with these examples and try to gain some intuition as to what these simple structures can and cannot do. Let me say one thing that I should have said at the beginning. So this is a picture of a vanilla neural net, or MLP, but in almost all important examples, you need some kind of architecture, some more sophisticated architecture. Okay. So examples are like convolutional neural nets, transformers, etc. So you don't get, as a mathematician, I kind of thought, oh, I'll just learn MLPs and then I'll be fine. But you discover very quickly that you need to spend some amount of time learning what a convolutional neural net is and learning how it works, and learning what a transformer is and learning how it works, etc. Yeah? These architectures are really important, and also they're extremely beautiful, I think, to get to know. Okay, so now I just want to discuss 5 examples of machine learning or deep learning being used on pure mathematics problems. So there's 2 examples of guiding conjectures. So these are in knot theory and representation theory. This is the work that was done with the DeepMind team. And then there's a beautiful example of Adam Wagner guiding search in graph theory. There's an example that I love in algebraic geometry, guiding computation. And there's another example in semigroup theory, guiding proof. So I should say that this is nothing like an exhaustive list, and this is nothing like the kind of best examples or anything like that. I just like these examples. I think they're illustrative. And I think that the more of these examples, both simple examples like I presented on the previous slides, and more sophisticated examples like I'll present here, the more we see these examples, the more we know where to go, and the more we have a sense of what will work and what won't work. I think our experience with this subject so far has really indicated that it's rather surprising what works and what doesn't work. Okay. And I think that there's an instinct that mathematicians have that somehow, there's this hype machine that tells us that deep learning is going to solve any problem. And so I regularly have people that come up to me and say, there's been this problem that I've been thinking about for a long time. Can deep learning solve it? And I think the only kind of reason that they think this might be possible is because essentially of this hype. But there's no kind of concrete idea, this is similar to another problem that's been solved by deep learning or anything like that. Okay, so I think it's very important to see these simple examples. So the first example is in knot theory. So you probably all know what a mathematical knot is. So knot theory is one of these subjects. So a knot theory, so a knot is a little bit like a number in its absolutely fundamental mathematical object, which is connected to an enormous amount of mathematics. So we have this whole world of 3 and 4D topology. We have these incredible connections to hyperbolic geometry after Thurston. So Thurston noticed that the complement of the vast majority of knots admits a hyperbolic structure, which is unique. And you can study properties of the knot by studying this hyperbolic structure. And also there's many other connections to quantum topology, mathematical physics, etc. And somehow knot theory is so large, a little bit like number theory or something, where there's many, many different approaches to the subject, and it's very easy to imagine that insights from one corner of the knot theory universe might help in another corner. Okay, this is somehow the peril of success. Your field grows so large that it's very difficult to know all the corners of it. So one of the reasons that knot theory is so interesting in terms of this, so one suspects that right across mathematics there's connections that we haven't noticed yet. But one of the reasons that knot theory is so interesting from the point of view of establishing unlikely connections is that knot theory has a wealth of invariants. So you can think of these as kind of measurements or shadows of the knot, which arise from these different worlds. So signature is a topological invariant, Alexander polynomial is a topological invariant, hyperbolic polynomial is a hyperbolic invariant, obviously. Jones polynomial, Humflick polynomial, A2 polynomial, these are all quantum invariants. So following the seminal work of Jones, 3 genus, topological 4 genus, both topological, etc. So these are all quantities, they're not so far away from being numbers. And you can ask, do there exist unexpected relations between these invariants? I think it's a very natural question to ask. So there's many relations known. Are there relations out there that we don't yet know? And do these relations point to connections in mathematics that we haven't yet seen? So in this work, so this is Alex Davies, Undras Juhas, Mark Lackenby, and Nenad Tomasev, prove that, so there's this quantity which is called the signature of a knot, which is a topological invariant. It's very easy to compute, and basically what they decided to do, I'm not quite sure why, there's many different invariants that one could attempt to relate in this way, but Andras Juhas and Mark Lackenby are both not theorists, and so I guess their instinct was perhaps signature can be predicted by hyperbolic invariance. So here you have basically a whole list of hyperbolic invariants with the exception of a few. And you try to predict signature from these other invariants. So this can be phrased as a very vanilla supervised learning task. Okay? And then they discovered that this signature can be predicted with high accuracy. And once you do that, you can do attribution techniques, which is like feature selection in statistics. You're asking which aspects of the input have the greatest effect on the output in my model. So I think this is done by a kind of vanilla gradient technique, namely taking the derivative of the learned function. So you approximate a function with the neural net, and now it makes sense to take a derivative, and this is telling you the directions in which your prediction is changing the most locally. Okay? And so you have a couple of these properties which are much more decisive in the output than the others, and then you try to mess around with the formula, build a conjecture, try to prove it. And my understanding is that they built a conjecture, tried to prove it, tried very hard to prove it, discovered it was wrong, found a modification, and then were able to prove it. Okay? So this is using deep learning as a discovery tool in mathematics. And also, of course, this theorem is a lot of work to prove. I think they work pretty hard to prove it. But still, it's very interesting that these techniques can lead one to look in a particular direction. So the next example comes from representation theory. So here, there's this combinatorial invariance conjecture, which I've kind of been fascinated by ever since I was a graduate student. It's a rather complicated statement, but I'll try to give you the bare bones of it. So we have X and Y, which are permutations. So just a pair of permutations of, let's say, 10 elements. And you can associate to this a Bruhat graph. And this association is not complicated. I mean, you produce a complicated graph, but this arrow is not particularly complicated. So basically, this is some part of the Cayley graph of the symmetric group. And, okay, so you can associate this complicated thing, like in an easy way, you associate this complicated thing. And now there's also this Kaczmarczyk polynomial, which is very simple, but somehow this arrow is extremely complicated. So this quantity in representation theory is of enormous significance. And basically, I would say that we understand this quantity reasonably poorly, despite 4 decades of work on these very mysterious polynomials. And the conjecture, the combinatorial invariance conjecture, says that from this object directly associated to X and Y, we can produce this polynomial. This is the combinatorial invariance conjecture. So, I don't know, I like to think about this as being the Bruhat graph is kind of like a tiger. I mean, the pixel values of a tiger. So if we'd grown up surrounded by Bruhat graphs, perhaps we'd be able to instantly predict what Kaczmarczyk polynomials are. So we trained a neural net to predict the coefficients of Kaczmarczyk polynomials. It did so very accurately. I think, well, at least from my point of view, shockingly accurately. And again, we were able to do some kind of attribution, saliency analysis of the learned model. And what this told us, so each of these boxes is indicating a particular edge here. And this saliency graph, which I still find really remarkable, is telling us that certain edges in this graph are much more important than other edges. And after enormous amounts of work, we got the following conjecture, which is known in many cases. So in particular, this conjecture gives a new formula for the Kaczmarczyk polynomial starting from the Bruhat graph. And this is a conjecture which should solve combinatorial invariance for symmetric groups. And I think it constitutes, I think, really significant progress on a problem that's about 40 years old. And I just want to point out somehow here, it's very interesting. So this term in this formula, so I'm not explaining what this formula says, but this formula is, so this bit of the formula is basically very human. So this I can look at and understand immediately, whereas this bit came out of the saliency analysis. So in this graph down here, this bit of the formula is referring to this bit, and this bit is referring to this bit, and somehow the saliency analysis pointed us to the non-obvious part. So one way of thinking about this is the graph that I've got to look at as a graduate student and try and work out what's going on. You know, it's just kind of hopeless, whereas the model tells us which edges to look at. And even though it might still look complicated, if you stare at this picture, you see a whole lot of cubes, which is very unexpected. So graph neural nets were used. So if you don't know what a graph neural net is, basically think that somehow the graph determines the structure of the neural net. We told the model all the casualistic polynomials above the base node. So we're giving the model rather a lot of information, but still that's allowed information for this problem. So without this information, the model didn't do so well. With this information, it does extremely well. And, oh, sorry, I repeated myself. So, you know, 99.7% accuracy on the coefficient of Q after I don't think a particularly long period of training, which is totally remarkable to me. And the inner gradient was used for attribution saliency. Okay, so in order for the team at DeepMind to say, Geordie, what's going on here? They used vanilla gradient on the model. Okay, so now we come to graph theory. So this is another example that I think is extremely beautiful. So graph theory contains many conjectures, and if you talk to graph theorists, I'm not a graph theorist, one gets the sense that there's somehow very deep and interesting conjectures, and there's a whole lot of conjectures that are just wrong, but no one can find a counterexample. And what Adam Wagner does is he says several of these conjectures are phrased as an inequality. So quantity X is bigger than or equal to quantity Y. And both of these quantities are derived from the graph. And so then you can rewrite this as, let's say, X minus Y is bigger than or equal to 0. And so now you can use that as a reward function for reinforcement learning. And so you now have an agent which is exploring the space of all graphs, trying to minimize a quantity. So maybe I'll just give a little bit more detail on what is actually happening here. So we take a complete graph on 20 vertices, say, and then Adam sets this up where you have a policy. So you're basically, the computer is given each edge one by one, and we say, would you like to take this edge or not? And the model tells us yes or no. Initially, this choice is made entirely randomly. And then, so you do your random sample of 1,000 graphs or 10,000 graphs. And then you look at those that have got the least so the least reward. You want to minimize the reward, for example. And then you use these as training data for a policy for your next rollout. So this is kind of very, very standard reinforcement learning, so called cross-entropy method in reinforcement learning. One of the things that I think Adam learned in this process is that there's many, many different roads to reinforcement learning. They're all very complicated, basically, and so he chose the kind of simplest one that could possibly work, because you often have issues of convergence and things like this. And I think this has also been our experience with the DeepMind team, that it's often very difficult to get reinforcement learning to work, and there's often very subtle kind of technical issues. And so if you can find a structure which is debuggable and simple, even if it's not the best reinforcement learning technique out there, it might be it might still lead to interesting mathematics. Whoops, I'm not sure why I repeated the slide. Okay, so here's an example. So GB, a connected graph, inequality. We don't really care about what the inequality says. All that we care is that we can rephrase this as the fact that a conjecture about a given quantity being bigger than or equal to 0, and we can try to minimize that quantity and hope for a counterexample. So what I'm showing you here is a video where, so each time we roll out our model, we generate a whole lot of graphs, and then we take the best, do an update, continue. And so what I'm showing you is a video illustrating 50 samples from each of these models, and every time we're sampling, this model is, in theory, getting better at producing a counterexample. So here it goes, and you can see it seems to be converging to some kind of structure. Okay, and then Adam plugs this back in, and this is indeed a counterexample to the conjecture. And I think that you know, one shouldn't underestimate the size of all graphs. So you can think that maybe one could just guess this graph. And I think that unless you're really expert, you cannot just guess this graph. I think you could have found this by other means, but it's not that easy. Here's another one, another conjecture. So again, we have quantities associated to a graph is bigger than 0. We can phrase this as a quantity that we want to minimize, and here we have a video of the rollouts. So of the samples from every update. Okay, and so here you see a very clear pattern arising. You have these petals and you have these long stems, and then Adam, so he plugs this back into his system. He discovers this is not a counterexample, but the value is very low, and then he thinks, oh, what happens if I add a whole lot of petals and extend these arms? And then he gets a counterexample. Okay? This is neural nets kind of pointing us in the right direction of where to look for counterexamples, which I think is very interesting. So here's another example. This is guiding computation, computing Gauss-Manning connections more efficiently. So this is some algebraic geometry. We have a whole lot of algebraic varieties defined by equations. So there's a family of hypersurfaces. So for example, so the example considered in the paper is the example of quartics in 4 variables. So this is quartics in projective 3 spaces. So depending on the coefficients, so the topology of this space stays the same, but the complex geometry varies, and the complex geometry is measured by the so-called periods. So there's a certain integrals which are extremely fundamental and very difficult to work out in general. And so in this problem, there's often simple examples of these quartics where, for whatever reason, you can work these out. So for a general one, you're not going to be able to work these out, but you can work out one at an easy point. And then there's a particular differential equation which tells you how to get the integrals here from the integrals here, okay, called Gauss-Manning connection. And the problem is that if you want to imagine that you've computed these here and you want to compute them over here, so you get some differential equation corresponding to a path from A to B, and this might take weeks, or you kind of have no idea how long this is going to take. But the funny thing in this world is that sometimes going from A to B takes a week, but going from A to C takes a second, and going from C to B takes a second, and this whole system is transitive. So this is the situation. You have a week going from here to here, you have here a second, maybe here's a minute, and you think maybe there's another point over here that takes a second and a second. Okay? And I think that these estimates of time are not so crazy. I think it's a very interesting problem because of these kind of vast differences in computational difficulty. So here, Kulkarni and Serters trained a vanilla neural net to predict computational time. So they trained both a vanilla neural net and a convolutional neural net, and they're able to considerably speed up existing computations. So based on the input, which is some kind of coefficients and some extra things, the neural net is able to predict within reasonable accuracy how long the computation is going to take. Or more accurately, they tried to predict, is the computation going to take under 30 seconds or not? So just from the coefficients of the polynomial alone, they weren't able to get good results as far as I can understand, but adding something that's easily computable, kind of first order approximation of the Gaussian-Manning connection, helped learning. So this is, again, this principle of it's very important how you give what features you allow the neural net to see. So their best performing method was an ensemble method. And what's interesting here is that they also compare it against standard statistical methods. So if you think about these methods, I think it's very, very good just to say, what would have happened if we'd done a linear regression or if we'd used standard statistical methods. So I think in the example of the two examples of Adam's work and also our work in representation theory, it doesn't really make sense because it's absolutely unclear how to fit a graph into a standard statistical method, but I think it's an interesting question. So guiding proof, so this is the final example. So here you're given a multiplication table, and I ask you, can you complete this to an associative multiplication? So in fact, what I've taken is the multiplication table of the 0, 1, 2, 3 mod 4, okay? But you don't know that, and you're asked to complete this to an associative table. And when you start thinking about this, this starts resembling like a Sudoku thing. So imagine that I placed a certain symbol here. Perhaps this would break associativity, and then you get this kind of branch and down problem. And so this is one of these problems where certain choices, just like in Sudoku, if you make a certain choice, it can just illuminate the whole situation, but then other choices can lead to very, very long proof trees. So Simpson shows that this can be attacked by a reinforcement learning. So the agent traverses, basically says, which of those question marks should we try to expand? He's able to obtain shorter proofs in some cases. He's able to rederive a classification of certain more potent semigroups, but also one needs significant training time. And I somehow I'm very much enchanted by these little gardens of mathematical proof. Okay, so I just want to finish with some just general comments. So these are more, so this is particularly for the mathematician. So there's one vanilla structure which is versatile on many problems. And the reality is that vanilla architectures usually only work out of the box on simple problems, in my experience. Architecture matters. And I just want to point out that, for example, in AlphaGo or in AlphaZero, there's this extraordinary tree search piece. And so, although we think about AlphaZero as being a neural net, really it is a neural net combined with this extraordinary tree search capacity. And so, I think in terms of ELO, just playing the neural net gives you ELO about at 3,000, and playing neural net plus tree search gets you up to ELO 5,800 or something. I'm sure Alex can correct me, but almost half of the content comes from tree search. And I think that one sees this in a lot of mathematical applications at the moment, that there's some so firstly, details matter, and also there's usually some kind of interaction with domain knowledge. So advice for interested mathematicians. So, details matter. I think it's extremely useful to work with someone who has background in machine learning. One thing that we've definitely discovered with the DeepMind team is that one needs to decide, are we pushing mathematics or machine learning? So if we're pushing mathematics, let's not be scared to use a very simple architecture to try to see what's going on. Or if we're pushing machine learning, let's try to push it on a problem in mathematics that we understand very well. So Alex gave a lovely talk in a seminar that we ran last semester in Sydney called A Technical History of Alpha Zero. And I found it really interesting that it began as a supervised learning task and slowly evolved from there. And one should have a precise idea of what one wants. Finally, the one thing that I kind of can't anticipate in this whole story at all is what is going on with scale. So again, this is kind of the point of view of a mathematician interacting with deep learning researchers. I often have the experience that we have some situation where things aren't really working, and then machine learning researchers say, let's throw a much bigger model at it. And I'm like, why? We don't understand. But the simple answer is that it works. And for me, it was very illustrative. Probably half the audience knows this, or 75% of the audience knows this, but there's this kind of watershed moment in machine learning, this AlexNet paper, where basically they showed that you could just get much better performance on the ImageNet classification problem by significantly scaling up architecture and putting a lot of work into number of parameters. So they write at the end of the introduction, all of our experiments suggest that our results can be improved simply by waiting for faster GPUs and bigger data sets to become available. And this is from a beautiful recent talk of Greg Yang, multiplying the number of parameters by 10 increases the training accuracy significantly. So I can very much imagine a situation in mathematics where this line is the line where you discover a counterexample to a major conjecture. Okay, so you're just never going to see this with your 13 million parameter model, but by scaling up, suddenly you reasonably easily find a counterexample. Okay, so that's what I learned from a fortune cookie in Sydney, and yeah, so. Just to sum up, I think this is, so neural nets can provide useful tools for conjecture generation and refutation, and I suspect that the next few years we'll see many more applications in pure mathematics, and I'm particularly interested in the kind of organizing calculation and guiding search, and thank you very much.
Yes, thank you very much for the amazing talk. We're going to take a couple of questions from the audience, if there are questions, comments, or suggestions. Sure.
Hey, Geordie, it's Kevin Buzzard. Oh, he can't hear me. Hey, Geordie, it's Kevin Buzzard. Can you hear me now?
Yes, I can hear you, Kevin.
So all your examples are about sort of concrete mathematical structures. Do you think these machines will ever figure out how to prove theorems autonomously?
I mean, I think that, so one of the reasons that I find the Carlos Simpson example so interesting is because he is exploring a proof landscape. It happens to be a very small proof landscape, but it is still, I think, a proof landscape where you're making decisions which particular avenues to explore, etc. Yeah, so my sense is yes, but exactly how, I have no idea. And I'm sure there's many more experts there.
But by the way, thanks for the talk. It was sort of just the kind of thing that I, as a mathematician, wanted to hear. The room is full of deep learning people. But I was very clear. Thank you very much.
Any? Oh, okay.
Can you hear me? Not sure. Tu as appuyé sur le micro. Yeah, can you hear me? I'm Sylvie Bensoni. I'm not at all an expert in these things. I was wondering about the example you showed us about graph theory. In the case where we can use AI to look for counterexamples, how do we know that there must be counterexamples? How do we know that these conjectures are false?
So I struggled to hear, but I interpolated the question as follows. How can we know that there's a counterexample? Is that roughly the question? We absolutely don't. So personally, I spend an enormous amount of time as a mathematician trying to prove stuff that's wrong. So I sit there, I'm trying to prove some lemma, and sometimes 2 days later I decide, oh, maybe I'll try one more example, and it's just wrong. So if I had a little kind of mental bicycle that I could put my problem in and it said, no, it's just wrong, Geordie, no need to waste the next 2 days of your life, that would be very useful. And if it doesn't find anything, then I can have some degree of certainty that I might not be wasting my time in some very obvious way. But yeah, we absolutely don't know that counterexamples are there, but still having a reasonably structured way of searching for counterexamples, I think, would be enormously powerful.
Okay, thank you.
Is there any other question? Yes.
Hi. The correlated feature map you showed us, is it handcrafted inside the model, or it's that like the model learned them alone? The feature map you showed us.
So I'm really sorry, I cannot hear at all at the moment. Like, I just hear noise, I don't hear any voice.
You showed us the feature map when you inside the graph, maybe the graph theory or something. So there is like a table of correlation feature map. It was the blue and red. So it's like handcrafted features, or it's like the model learned the feature alone?
Okay, so I understand from the chat, so you're asking to what extent is the feature map handcrafted and to what extent is the model learning it? So yeah, this is a good question, and I was trying to emphasize that, so the example with the symmetric group is meant to emphasize that the features really matter, but I think basically the point of deep learning is that features are learned. I'd really recommend, so there's this book of Corville, Bengio, and Goodfellow called Deep Learning. And they explain this point of view on deep learning where you start off with the kernel method, and then you want to learn your embedding, and then you want to learn that embedding, and then that leads to a deep neural net. So I think that one very good way of thinking about deep neural nets is as iterated learning of features. So it's very important that you put enough stuff in there to separate out so that it can, but then you hope that it does learn learn features relevant to the problem.
Okay, so it's not like a mathematical known features, like you put names there, so each feature have a name in mathematics. So how did you know that inside that graph that's the feature in mathematics?
Yeah, so definitely you should also ask Alex Davies this question, but my impression is that basically you just try to give the model as much information as possible. So anything that you think might be relevant, give it to the model, because you can always later on, if you have something training well, you can take it away and then see if it still does well. So in the Gauss-Manning connection example, they first tried on monomials, weren't successful, and then they added a whole lot of stuff. And then finally they decided that there was only one thing that they were adding, which is this infinitesimal or order 1 Gauss-Manning term that ended up being significant. And I think, for example, in the knot theory, they put in a whole lot of different hyperbolic invariants and a whole lot of other stuff and saw, you know, can we predict signature? Okay, we're predicting it with reasonable accuracy. What's actually important? So it's much better to give it too much than too little.
Okay, thank you.
Hello, my name is Amari Hayat. Thank you for this very interesting talk. I had a quick question. So you've showed us several very interesting problems. How did you choose the mathematical problems you wanted to study with deep learning?
Okay, so I think I could interpolate that question as how did we choose these problems? My neural net is doing very well at the moment at this stable diffusion. Okay. How did we select the problem? So basically, I think that we started off having absolutely no idea and just got lucky on, you know, we tried some things that didn't work and then got lucky on some other things. But I think that the principles that I outlined should guide us more accurately in the future. So I think it's very good to have some kind of basic notion about what kind of functions deep learning likes to learn. And yeah, and I think that it's extremely important just to be aware of what people have tried, and that we're clear about what we've tried and what we haven't, what we've tried and what has worked, and also that we're clear about what we've tried and what hasn't worked.